So, before anything on the page, I think I want to describe a function. So what is a function? A function is any rule which takes an input and gives you a unique output as long as you know what the input is. And here's one such function. So, imagine you want to start on a circle, centered at 0, 0, up a radius 1. So you're starting there at 1, 0. So start there. And now pick an input theta. I need to describe a way to get an output. And here's one. Start at 1, 0, and walk counterclockwise. Across the circle. The total length of theta. So someone's going to tell you how far to walk, and you'll just walk around in a circle until you cover that much distance. There is some distance theta. You'll land at some point. You'll land at some point x, y. Here are two definitions. Cosine of theta is the function that recovers x. Sine of theta is the function that recovers y. So I guess here's one question. Do those actually seem like they're functions? For any input, can you determine an output? Yeah, just walk that distance, figure out where you land. I guess maybe you're worried that, like, what if x is negative, but that just means walk the other direction, right? So these are two functions. These are the functions we'll be studying for basically the rest of the semester. The study of trigonometry is the study of the trig functions sine theta, cosine theta. How are they described? Start at 1, 0, walk some distance theta. We'll cover the x-coordinate and the y-coordinate. Those are cosine and sine. So that's all I'm going to say about sine and cosine today. What I want to focus on today is instead angles. What is this argument inside of the trig function? So, let's start talking about angles. And, well, let's start with something that you just already know. Let's talk about degree measure of an angle. So, you already know what, like, degree measure means in some sense. How big in degrees is an angle that goes all the way around the circle?
360.
360, yeah. And that's just a convention. One full rotation is set to be 360 degrees. So what should an angle of 1 degree mean? It's just like 1/360th of that. Yeah, and that's all. That's what a degree is. 1 degree is 1/360th of a full revolution. So if you start rotating the circle, but you only go 1/360th of the way around, that's a degree. So with that in mind, let's write down what a 90-degree angle should mean. So a 90-degree angle should be 90/360ths of a degree. 90/360ths of a revolution. Well, let's simplify that. What's 90 over 360?
4.
Yeah. So a 90-degree angle is 1/4 of a full revolution. On the other hand, you already know what a 90-degree angle is. It's like, that's a right angle. Is that the same as 1/4 of a full revolution? Yeah. There's 1/4 of a full revolution. There's another. There's another. And then there you are, back to where you started. So yeah. So great, that's not news to anyone. You know how to measure angles in degrees. But there's like a weird choice in it. Like, why should 1 degree be 1/360th of a full revolution? Why are you breaking a circle up into 360 equal parts? And the truth is there's no good reason to. Any number would do just as well. The reason we do it is because the Babylonians did it. The reason the Babylonians did it is because they liked the number 6. If the development of the same stuff had happened more recently, then we would probably be breaking the circle up into either 1,000 or 100 equally sized pieces. Same reason that there are 60 seconds in a minute. Like, there's no good reason to break a minute up into 60 equally sized pieces. It's an arbitrary choice. So, I'm about to develop a way that doesn't involve this arbitrary choice of breaking a thing up into a bunch of equally sized pieces. Let's measure angles by doing geometry. This will look up at the so-called Radian measure of an angle. And let me give you like the upshot and downside. The upshot is that there's no arbitrary choice I'm going to make. Everything will be geometric. There will be no decision that I just have to make at some point. The downside is numbers will much less often be like whole numbers. There will be a bunch of pies that will start appearing at this point in the class. So, let me give you a definition. So, stand on a circle of radius r. At any point on that circle of radius r. Walk counterclockwise around that circle until you come at a distance s. So, you're standing on some circle. That is a perfectly round circle. You start somewhere. And you just start walking around until you've covered a total distance of s. The measure of this angle is s divided by r radians. So as a consequence, like I'm not making any decision to break the circle up into a bunch of equally sized pieces. I'm just saying we'll cover the distance of that arc. That gives you the radian measure of that angle as a ratio. That makes sense? Like as a definition? Maybe let's just do some examples. Here's one. You draw an arc length of 2 centimeters on a circle of radius 2 centimeters. What's the radian measure of that angle? Well, yeah. It'll be... I'll usually use the Greek letter theta for angles. Generally, I'll use Greek letters for angles, not all the time. Right, it will be s divided by r is 2 centimeters divided by 2 centimeters. And yeah, that's 1 radian. So you notice that, like, it seems like this should be a unitless quantity. Like, the centimeters cancel. So radians are a unitless quantity in some sense. They don't have a unit to them. You just say the word radian to remind yourself that you computed this as a ratio of arc length by radius. You feel pretty good? Same thing, but for that one. Arc length 6 centimeters, radius 1.5 centimeters. What is the arc length? You do the division again. Yeah, that's better. 4 radians, that's what people get? Nice. So, radians are a much more natural unit of measure to use when you're talking about angles, in that there's not this random choice. A lot of times if you're thinking about applications, degrees have the nice property that when I tell you an angle is like 1,000 degrees, you can like picture how big that is. That's about 3 times all the way around the circle, but not quite. If I tell you, here is an angle of 8 radians, you kind of need to think hard to figure out how many times around the circle that is. It's slightly more than once, as we're about to see, but you have to think about it. So there's the upshot of degrees versus radians. So let's talk about converting between them. And to convert between them, let's convert everything into full revolutions. So the goal of this page is how do you convert between the various ways you might measure the size of an angle. So let's start with this. Let's try to figure out how many radians makes one full revolution. And I don't know, how many people just like already know the answer? What do you think it is?
So 2 pi.
I think it might be 2 pi. Let's figure out why. Sorry, radians mean something about the ratio between arc length and radius. So I guess that means if you walk all the way around the circle, the ratio of this to this should be 2 pi. So let's see exactly that happen. All right, so let's imagine walking counterclockwise all the way around the circle. So you start at some point on a circle of radius r. You walk all the way around the circle. You would like to know how many radians that is. What's the formula for the circumference of a circle? 2 pi r. So the arc length of this is 2 pi times the radius. Oh, neat. So now I can compute the radian measure. Radian measure is s divided by r. So the radian measure is s divided by r is 2 pi r over the radius is r. Yeah, that's 2 pi. There's the reason that one full revolution is 2 pi radians. That idea make sense? Nice. So now let's use that to capture this next thing. Let's talk about how to convert from the measure of an angle in degrees to the measure of an angle in radians. So just like how in order to convert from like miles to kilometers, you basically just need to know what 1 mile is in kilometers or vice versa. Same thing here. That's what we'll figure out. We'll try to figure out how many degrees to a radian. Here's how we'll do it. So let's try to compute d degrees, and let's try to have something that involves radians on the other side. So in order to do that, I'll try to do some conversions. How many degrees make a full revolution?
360.
360. That's the way degrees are made. You break up one full revolution into 360 equally sized pieces. According to what we just did, how many radians makes a full revolution? 2 pi. Nice. So d degrees. So here's the game I'm playing. I'd like to know what d degrees is in some other units where I want to like multiply and divide by something that'll convert away from degrees. So I needed to get rid of degrees. So I'll multiply by 1 revolution over 360 degrees because that whole thing is just 1. You can multiply and divide by 1, that doesn't change anything. You can multiply by 1, that doesn't change anything. Similarly, this is 1, and now you see the revolutions cancel. And so what are you left with? You're left with d times 2 pi over 360 radians. How did that feel? That feel pretty okay? Nice. Should that be simplified? Do the numerator and denominator in that fraction have any common factors? 2? Right, 360 is even, and I see a 2 on top. So I think I would want to rewrite that as d times pi over 180 radians. So that means that d degrees is the same thing as d times pi over 180 in radians. So if you want to convert from degrees to radians, here's your instruction for conversion. There's the constant of conversion, pi over 180. You want to go from degrees to radians, multiply by pi, divide by 1. That seems pretty okay? Nice. You could also do it with 2 pi over 360, but then your answer would always be more complicated than it needs to be. So you may as well not do that. Think we could go the other way around? In fact, let's try to do it without going through those same steps. So if you can plot from degrees to radians by multiplying by pi and then dividing by 180, what do you think you need to do to convert from radians to degrees? What's the opposite of multiplying by pi and then dividing by 180? Multiplying by 180 then dividing by pi? That seems reasonable, I think. And yeah, there it is. If you want to convert from radians to degrees, then take the radian measure you have, multiply by 180 degrees, then divide by pi radians. That idea seem pretty okay? Nice. And hopefully nothing too big yet. So let's talk about what you could, well, I guess a natural thing to do is let's just go through some examples. Let's try to hit these. All right, what is the radian measure of a 30-degree angle? And I guess I'll follow my thing with these examples. I can talk or you can just do it and we can come together. Should I talk? Okay. I'll wait a minute. You'll tell me how many radians 30 degrees is. Space. Let's see, I see some people looking at their calculators, which is fine. I'm going to want the exact simplified answer as well. So, what are people getting?
I got 30 pi over 180.
Sure. Is there any simplification you could maybe do to that? Yeah, I guess at a minimum, both the numerator and denominator are multiples of 10, right? Sorry, 30 is 3 times 10, 180 is 18 times 10. So you can cancel the times 10s. So there's a little bit simpler. Numerator and denominator still have any common factors? Yeah, 18 is 3 times 6. So you could simplify this further as pi over 6 radians. That agree with what people get? Nice. So 30 degrees is pi over 6 radians. Let's do more. Let's compute the degree measure of an angle of pi over 5 radians. So, if you have an angle of pi over 5, what do you need to do to convert that to an angle in degrees? I need to multiply by something and then divide by something, right? Excellent. So that should be the same thing as pi over 5 multiplied by 180 divided by pi radians. And now I guess the game is just simplified. I see a pi in the numerator and a pi in the denominator. Can cancel those. 180 is a multiple of 10, 5 is a divisor of 10, so obviously those cancel. I think you wind up with 46 at the end. Because right, multiplying by 10, then dividing by 5 is the same as multiplying by 2. So dividing by 5 is easy as long as you're okay with multiplying by 2 and moving a 0 over. People feel good? Alright, let's do one last one like this. Let's try to lawn the radian measure of a right angle. So, right. There's a right angle. Let's try to figure out its radian measure by using that. It's 90 degrees. So 90 degrees to convert, I need to multiply by pi, divide by 180. And 180 looks like they have some stuff in common, so that simplifies it a little bit. What's that simplify to?
Pi over 2.
You want pi over 2? People happy? Yeah. So on the one hand, there are some computations that we've just done. Some of these are things worth internalizing. An angle of 30 degrees being the same as an angle of pi over 6 is something that we'll use an awful lot. So that's something that's eventually just worth having internalized. We'll do the conversion later on again. The fact that a right angle is 90 degrees is pi over 2 radians is another important fact that will come up quite a bit. So these are, on the one hand, easy computations to do, but they're facts worth just having on hand without having to think about. Cool. So what are we going to do with these things now? So let me give you a list of the topics that I want to hit for you. So we've talked about arc length. In fact, arc length is super easy if you're walking in radians already. And if you want to think about arc length, well, you can use the fact that the radian measure is equal to arc length divided by radius. Does that look like something that you could conceivably solve for the arc length? Yeah, so as long as you're on a radian measure, you can figure out the length of an arc that you walk on a circle immediately, basically. There's another thing that you might want to do, and let's do that. Figuring out how much area is in this, a slice of a circle. So let's do that. Start with suppose you have a blueberry pie. Being a pie, it is, of course, circular. Its radius is some quantity r. And let's suppose that you cut out a slice from that pie whose angle is pi over 4 radians. Let's try to compute that area. So let's just try to do it. If I were to take the area of the full pie, that would be the area of a circle of radius r. What's the formula for the area of a circle of radius r? This is the type of thing, this formula that either you remember right now or you don't. Either way, I'm about to write it down. Alright, done. So the area, so just like how you told me the formula for the circumference of a circle is 2 pi times the radius. The area of a circle of radius r is pi r squared. which admittedly I think I made this joke last time, but pi r not squared. Pi r round. Convoid r square. Got a chuckle. More than it dissolved. Alright, so we have that down. So we have the area of the total pi is pi times the radius squared. I want to know the area of this little round slice of the pie. So let's try to figure out how many times this red slice of the pie goes into the full pie. What's the radian measure of the angle that would go all the way around the circle? Yes, say that over. 2 pi. They were still pretty quiet. So a full circle has 2 pi radians. So how many times does this slice fit into 2 pi? How many pi over 4s does it take to make 2 pi? And I guess that's like a division problem. On the other hand, like maybe you can just eyeball it and say, well, it looks like 8. But I want to do it in more generality next time, so I want to write down the division. So how many times does this piece of the pie fit into the whole pie? Well, that's the same as 2 pi divided by pi over 4. And you do that division, what do you wind up with? Well, it's like complicated because there's a fraction in the denominator maybe, so that's the same as 2 pi times multiplied by the reciprocal. Yeah, beautiful. Thank you. I was about to ask that. Nice. So this small piece of the piece of the pie, fits into the whole pie 8 times. So it must have 1/8 of the total area. So the area of that little piece is the whole area of the pie divided by the number of pieces that we've cut the pie into. So I guess that's pi r squared divided by 8. How's that idea feel? Nice enough? There was nothing special about the fact that you're cutting these into slices of angle pi over 4. You could do this for absolutely anything, right? And there was nothing special that the circle happened to be a pi. That was just so as to motivate the bad joke about pi and what is convoid. So let's try to do another one. So suppose you have a circle of a radius r, and you cut out some angle of measure theta, where theta is just some number. As the class progresses, you'll have to forgive worse and worse pictures of circles. That point where the lines meet is supposed to be exactly the middle of the circle. Let's try to figure out this area. And we'll go through the exact same steps. So a full circle has 2 pi radians in it. So if you want to find how many times this slice of the circle goes into the full circle, that's a division problem. How many times does this little area go into the whole area? Well, it goes into it 2 pi divided by theta times. Right, that's just what division means. How many times does a thing of this size fit into a thing of that size? That's what division does. Nice. So if you want to find the area of this slice of the circle, then start with the area of the full circle. Still pi r squared, same as it was above. If you want to find the area of this piece, which, I'll drop the vocabulary again, but that piece is called a sector. It's the whole area divided by how many times your piece fits into that area. So pi r squared divided by 2 pi divided by theta. That look like something that should be simplified? Yeah, well, now it doesn't. fraction in the denominator, so let's multiply by the reciprocal instead. That's the same thing as pi times the radius squared times theta over 2 pi. So on the one hand, that's like a perfectly good formula. I could put this on the next line under that Phelan statement. But I think I'd rather simplify that formula to something that's easier to use. What's that simplify to? Well, if you want to do, like, write it as a single fraction, it would be pi times the radius squared times theta divided by 2 times pi. Do the numerator and denominator have a common factor that you could cancel? Yeah, what's that common factor? Pi. We can cancel the pi. I don't think I see any other simplification. I don't know that theta's even a lot or anything. The radius could be whatever. So I think that's the best I can do. The formula for a circle of radius r, if you start with a circle of radius r and draw a sector of angle theta, then the area of that sector is r squared theta over 2. If you have some sector whose area you want to compute, there's a formula that does the job. That make sense? Now notice, it was really important in that we walked in radians instead of degrees. And somehow the pi that shows up because you're walking in radians canceled nicely with the pi that shows up because of the area of the circle. So this really is the nicest possible formula. It would be uglier if you walked in degrees instead. Hence the remark, if someone gives you a problem where you're given the angle in degrees instead of radians, you could just walk out a formula. But maybe instead I would advocate just convert to radians and then use the formula that's above. Make sense? Let's do some examples. So suppose you have an angle of 1 radian inside a circle of radius 1. How much area is in that sector? And, well, we have a formula. It's r squared theta over 2. What is the radius in this problem? 1. So it's 1 squared times theta. How big is theta? 1. And then I divide by 2, and that simplifies to 1 over 2. Yeah, a half. Awesome. That seem nice enough? Let's see what happens in degrees. In this example, let's suppose that you have an angle of 1 degree in a circle of radius 20. How much area is in that sector? So I guess step 1, do we know what this angle is in radians right now? Can we figure it out though? Let's start by doing that. So first, let's, right here, convert to radians. So it's there with 1 degree, convert that to radians. How do you convert from degrees to radians? Looking at the previous page if necessary.
Degrees times pi over 180.
Awesome. And maybe a good way to believe that is if 2 pi is all the way around the circle, then pi is halfway around the circle. How big a degree is halfway around the circle? 180. So that's another way of seeing that same conversion factor. All right, so that's pi over 180 radians. Now do I know the angle theta in radians? Sure do. So I guess now we can just compute it out. Radius is r squared theta over 2. What's the radius?
20.
20. So this will be 20 squared times theta. What's theta?
Pi over 180.
Pi over 180 over 2. So on the one hand, like, there's an answer. It can probably be simplified. Maybe you would just want to use a calculator to get a decimal approximation. I guess I'll see what people would want to see. How many people feel that, like, given 5 minutes of calm focus, they could simplify that maximally as a fraction? How many people feel like they would struggle to do that in 5 minutes of calm practice? Okay. Then I think I won't. Let's just get a decimal approximation. What is that about? Well, guess it's a waste then. $20 squared. Maybe you would just notice that 20 squared is 400, but I haven't. Times pi. Then I divide by 180. Then I divide by 2. Oh, that's kind of nice. The Google calculator gives you, like, the parentheses that it's interpreting you as having there. Is that the thing that I actually wanted to compute? All right. Looks like the total area is somewhere around 3.5. Oh, let's think about units. When I gave you the radius of this circle, did I give you any specific units? No. Let's imagine I had, I don't know, inches. I've been doing a lot of metric. Let's use random imperial units. Then I guess the area of the circle would be 3.5 square inches. That seem good enough? All right. In a lot of the problems, I won't specify units in my radii just because I don't care that much. I'll try to do that in problems that are actual applications. All right, so the last topic I want to hit in 13 minutes, good, so I have lots of time, is the idea of angular speed versus linear speed. So here's the motivation. Suppose you have some real log units spinning around. There are two different things that you might think about. The point at the edge of my finger, how fast is that moving? That's like inches per second kind of thing. In 1 second, how big an arc does it trace out? The other thing that you might want is how big an angle does my shoulder trace out? Those are two reasonable measures of velocity of something spinning around. Clearly they're related. Let's write down the relationship. So, let's do it. So suppose you have a circle. Maybe it's a wheel or a gear rotating about some central axis. The angular speed in radians per second is given by, well, how do you talk about speed? It's how many things happen per unit time. How large an angle is traced in t seconds divided by t seconds. All right, just like you would measure any sort of velocity. How do you measure the velocity of a car? You say, well, how much distance does the car travel in t seconds? Then divide by how long you let the car go for. Make sense? Same thing with linear velocity. The linear speed is given by how long an arc is traced in t seconds. Then divide by how much time you let pass. My handwriting kind of degenerated there, but I said everything, so as long as people have anything written down in handwriting they can read, that's good enough for me. People doing okay? So let's talk about how to convert between them. So let's suppose, I'll draw a picture. You have a gear, which I will draw as a perfect circle. It should have teeth, but it doesn't. Of a radius exactly 1 thought foot. And let's suppose it's spinning at some angular velocity of 2 radians per second. Let's try to figure out what the linear speed of this gear is. So let's think of it this way. So this definition says, well, wait some amount of time and then divide by the amount of time you wait. So let's wait exactly 1 second and see what happens. So let's suppose that you wait exactly 1 second. This gear is spinning 2 radians per second. So in 1 second, how large an angle is traced out by this gear? If something goes 2 radians per second, and you let it go for 1 second, then how many radians has it gone? 2, right? Like that, yeah. That's what speed means. 2 radians. And remember, we have this conversion. If you know the angular measure of it, the radian measure of an angle, that's equal to s, the arc length, divided by r, the radius. So let's try to determine the arc length of this thing. Do I know what the angular measure is right now? Yeah, it's 2. Do I know what the radius of the circle is? Yeah, it's 1/3 foot. That look like we could solve that equation for us? Yeah, let's do that. So let's take this equation. I'll put it over here and plug in the particular things we have. So 2 radians is equal to the unknown arc length divided by the radius. The radius is 1/3. That look like you could solve that for us? Yeah, what's this? What are people getting?
Yeah,
0.66, sure. And maybe that tells you even what the exact answer is. It's probably like 2/3. Yeah, because what could you do? You could multiply both sides by 1/3. Oh, and maybe I'll even like be a jock and say, well, what are the units on this? Yeah, great. Because there's the formula you would have. 2 is equal to s divided by 1/3 foot. So the foot would get multiplied to the other side too. All right, so now let's just finish putting this together. In 1 second, this thing traveled 2/3 feet. So what is its linear speed? So in 1 second, it traveled 2/3 feet. How much so like 2 feet per 2/3 foot per second then? Yeah, awesome. Nice. So, we could have done, there was nothing special about the 2 and the 3, right? This could have worked for anything. There's going to be a general conversion from linear to angular speed. Linear and angular speed are related by the formula that the linear speed, v, is equal to the angular speed, omega, times the radius, r. And again, it was really important that we were measuring that angle in radians, right? Otherwise, we wouldn't have this formula to work with. So you could do this in degrees if you wanted to, but your answers will all be ugly, right? So just first convert from degrees to radians and go from there. So the last thing I want to do is I want to think about spinning gears. And I might not make it all the way through this particular example. I hope to make it at least a decent way through. Yeah. All right, so suppose you have a gear of a radius 5 inches spinning at 6 revolutions per minute. Let's try to compute its linear speed. Well, that's great. We have a formula that converts from angular speed to linear speed, don't we? So what do I develop? But it requires the angle to be in radians. Is the angle we have in radians right now? No, it's in full revolutions. But how many radians makes one full revolution? 2 pi. Yes. So one full revolution is 2 pi radians. So if you're going 6 revolutions per minute, really you're going 6 times 2 pi radians per minute? Does that make sense? And I don't know, that should be simplified, right? That's 12 pi. Nice. All right. So now, do I know the radius of this circle? I hope so. It's 5 inches. Do I know the angular speed of this circle in radians per unit time? Nice. That means I can use this formula. Velocity is omega times radius is 12 pi radians per second times the radius, which is 5 inches. Oh, not per second, per minute. Oh, yeah, thank you. Sorry about that. That look like we could compute that out? I guess so. 5 times 12 is 60. Can't do anything with the pi, so I'll just leave it be. 60 pi inches per minute. That answer make sense? In seeing that answer, would you want to simplify it in any way by using a different unit than is given right now?
An hour?
I think I'd want to do it in seconds. Yeah, otherwise, you could. There's nothing wrong with that idea. But 1 minute is 60 seconds, so. You could just as well. There's not, converting it to hours wouldn't be long, and in fact, like that would be, no, the standard SI unit, if you're publishing a science paper, should be in seconds, not hours. So, depending on your application, maybe you are interested in time scale of hours as opposed to seconds. That final point isn't the main point. Cool. You feeling pretty good? So, I think I'm running a bit shy on time. So maybe I'll stop here. I'll encourage you to take a look at the homework assigned today, which I did actually post. Did people get a notification that I posted the homework at some point today? Do you get notifications when I publish homework?
Yeah.
Okay. Okay, that's good. Take a look at those, take a look at these examples. Feel free to ask me any questions before the next time we meet, but also at the beginning of class on Wednesday would be good. Yeah, but I guess if it simplifies to like an easy number to write down, that I'm interested in the exact value.
Like for changing the base, it should just be like directional.
Yeah, but then go back. So your final answer should be a single logarithm.
So is that a single logarithm that just be one thing like that, or is it? I think I'm getting like a fraction.
Yeah.
Answer, right?
So there's just one last step. So I think the fraction, do you know what fraction you're getting on the top of your head? Okay.
I mean, like I said,
Oh, you remember how you did it, right?
I'm trying to know. Was it?
Okay.
I feel like
You said the right thing.
yeah, I was like X array, and then they both have a log base of 10.
Yeah. So the secret is it doesn't matter.
Okay, I think I wrote B, and then I tried to get an actual number at the end. So okay, cool. So that's.
So you get that log onto. And then what did you do?
And then I think I just multiplied these. Got a log of 12 and a log of 6.
Ooh, logs don't multiply like that.
Okay. I thought if they're the same base. No?
So here's the formula we do have. But there's nothing special about multiplying logs. Is there anything that's cancelled? So if you log of 1 divided by log of 2. And one last thing you should notice. Not quite. Think about the change of base value. So the change of base value says that the log base is log A divided by log B. So whenever you see a base you don't like, you can turn it into a fraction. But whenever you see a fraction of log, you can change it back to this. So how could you?
So I can go back this way.
Yeah.
So that's what you're. That's what I'm trying to do. So, are these gonna for all these examples? Is there gonna be one that cancels out? Then?
Yeah, almost everything will cancel out.
Okay. Like it'll be this kind of this way.
Yeah.
Oh yeah. I think I just multiplied it. I'm gonna take a picture.
So, as folks are just showing up, any questions people have on their mind? Yeah.
Can I take the quiz tomorrow at 9?
Yes. Did I reply to you? You sent me an email, I saw. Did I reply to it?
I didn't send the.
Didn't you?
So,
I could swear.
So you sent me an email to send you a schedule of my schedule?
Oh, okay, yeah. Yep.
But I did not reply to that.
Okay, you didn't reply to that email. Okay, cool.
You want me to?
What time did you just say?
9.
9. Send me an email with that in it. Cool. Yeah, you too. How good is playing buddies? Good. See, somehow the intent I have when I assign homework or spring break is to basically have the deadlines at like spring break is a week that doesn't exist. So anything that will have a deadline of a spring break, you just get an extra week that's assigned over. So I think that means that there And then I think I stretched it a little bit more. I think I said so there aren't any actual deadlines today. I think.
Yeah, there's no deadlines for today.
Okay, excellent. So there's nothing new today, but people have any questions they'd like to ask about Humboldt right now?
Question, you said like one that's coming in the Bible, or is it midterm?
Yeah, it's midterms.
Okay.
So the next midterm will cover like a bunch of the logs and exponential stuff.
Okay.
And then some of the stuff that we're doing, it's not immediately. So there will be like the trigonometry and starting on this.
Oh, okay, gotcha.
Yeah. You taking a quiz right now, Phil?
Yep.
Okay. Excellent.